Hello everyone, welcome to the Exam Ignite. Today I am continuing the next module 2 of the Electromagnetic Theory, BEC401 subject code. The second module is about Gauss law and divergence. The first module is already uploaded and please check the description box for the link. In this module, we are going to discuss about Gauss law, applications of Gauss law on the line charge, surface charge, volume charge, and point form of Gauss law and the integral form, and then divergence, Maxwell's first equation, and electrostatics, vector operator, divergence theorem, energy expanded or the work done in moving a point charge in electric field, the line integral current and current density, continuity of the current. This is a part 1 where I will be discussing the Gauss law completely. So the module 2 starts with the Gauss law. For the part 2, you can refer the description box. Gauss law, the total electric flux through any closed surface is equal to the total charge within the surface, regardless of how the charges are distributed and contributed to the flux from the charges outside the surface is 0. So here consider a closed surface. Let Q be a point charge at the point O. Consider a closed surface of any arbitrary shape which encloses the charge. Consider a surface area, that is ds, at the point P. Let R be the distance from the O. Let AR vector be the unit vector along the OP. So now we know that by the Coulomb's law, the electric field intensity at the P, it is given by the formula E vector is equal to Q divided by 4 pi R square AR cap. Consider that as equation 1. Next, electric flux density at P. You have to find. That is what we know, D. This is all explained in the previous video how we got this formula, which is equal to epsilon naught into E vector. E vector. That is equal to what? Electric field. That is Q divided by 4 pi R square AR cap. Consider this as equation 2. Now we have what? ds vector is equal to n cap into ds. So electric flux is given by d psi. D psi is d vector dot ds vector. That is, on substituting d vector to this equation, we get Q by 4 pi R square AR cap into n cap into ds. So what is d psi? D psi is Q divided by 4 pi R square. So the cross product of the dot product of AR cap into n cap is 1 into 1 into cos theta, which is cos theta ds. Total flux we have to integrate. This is a surface integral. So psi is equal to integration of small size, that is differential sign, that is surface integral of Q divided by 4 pi of ds cos theta divided by R square. Substitute that. That is a solid angle d omega. So psi is equal to Q divided by 4 pi into integral of S d phi, d omega. On next part is total solid angle, that is subtended by a closed surface at that point, is given by what? Surface integral of what? D omega. That is what equal to, always it is equal to 4 pi inside a closed area. So what we get? Psi is equal to Q. So replace the psi with Q. So psi is equal to surface integral of d psi, that is surface integral of d vector dot ds vector. So on replacing the psi as Q, we get the equation, Gauss law equation, as integral of d vector dot ds vector is equal to Q. This is all about Gauss law. Next comes the many charges. So case 1, if we having many charges inside the surface, when we get psi is equal to summation of all those charges. Case 2 is continued distribution of the charges within the surface, then psi is equal to in volume integral of rho v into dv. So but we have what psi is equal to integral of small d phi d psi, that is equal to integral of d vector dot ds vector. Finally you will get it as the surface integral of d vector dot ds vector is equal to volume integral of rho v into dv. Then what are the charges outside closed surface? It is obviously 0. Application of Gauss law. First application is field at a point to an infinite line charge of uniform line charge density. So consider there is an infinite line charge along the line AB. So rho, it is a uniform charge density that it is having. Let P be a point that is located at a distance of r from the line charge. Then imagine imagine a hollow cylinder around it with a cylindrical surface of radius small r, and there is a length of L, and both the ends are closed. Now closed surface is equal to what? We have learned it is a Gaussian surface. Now D vector be the flux density at this point B or point P. Now the flux density is what? It is constant over the surface. Hence it is equal to D vector. Now electric flux through this ds is what? D psi is equal to d vector dot ds vector. We know this. So now let ar vector and n cap, ar cap and n cap be the unit vectors along the d vector normal to the ds. So we can write it as d psi is equal to d into ds ar cap into n cap. R cap and n cap are parallel. In this diagram, we can observe r cap and this n cap are in parallel. So what dot product of ar cap into n cap will be what? 1. So d psi is equal to d into ds. Total flux means what? We have to integrate. So xi1 is equal to what? Integration of d psi. That is equal to what? Integration of ds. D into ds. That take the constant over the surface, curved surface as outside, and integration part will be only ds, which is the area of the curved surface, which is equal to cylindrical closed surface curved surface formula area is 2 pi rl. So substitute that. So xi1 is equal to d 2 pi r. Now we have got for the curved surface area. Still we have to go for top and bottom, lower flat surface and upper flat surface. So flux through the ds will be what? D vector dot ds vector is equal to d into ds into ar cap into n cap. Now the dot product of ar cap into n cap is 0. So what our whole d psi will be 0. Total flux through the upper flat surface will be 0 and total flux through the lower flat surface will be 0. So similarly, the total flux over the entire Gaussian surface will be what? We have to add the three surfaces also. 0, 0, so that gets added to d 2 pi rl. We have what? Psi is equal to q, that is linear charge density into length enclosed. So equate those two. D 2 pi rl is equal to rho l into l. L and l will get cancelled. D can be expanded as epsilon naught into E. Substitute that and write the equation in the form of E, that is rho l divided by 2 pi epsilon naught r. E vector will be equal to rho l divided by 2 pi epsilon naught r into AR cap. This was our first application. Second application is field at a point due to uniform charged infinite plane sheet. So consider a uniformly charged infinite plane sheet. So rho s will be a charge and charge divided by unit vector. Let E vector be at P, point P, located at a normal distance of r from the plane. Imagine that it is a right circular cylinder surface with both the ends are closed. Consider S be an element, ds be an enclosing area, P on the top of the flat surface. So D vector will be your flux density at that point. D psi is equal to D vector dot ds vector. So what will D psi is equal to AR cap and N cap are the unit vectors along the D vector. They are parallel, hence the dot product is 1. So it becomes D into ds. Total flux we have to integrate. On integrating, remove the constant outside, that is constant over the flat end. Next, area of the flat end will be ds. So xi1 is equal to dA. Similarly, for the xi2 also it will be dA only. Flux through that ds will be what? D psi is equal to d vector dot ds vector. Now the dot product is 0. So d psi is equal to 0. Total flux is adding all those, we get 2 dA. So we know psi is equal to q. Substitute q as rho s into a. So on substituting phi as dA, d as epsilon naught e to epsilon naught ea, that is rho s. So E will be rho s divided by 2 epsilon naught. Field at a point due to the spherical shell of charge. This is the first case we are considering when P is outside the surface. When the point P is outside the closed surface. Consider a spherical shell of charge with a uniform density, uniform distribution of the surface charge. Rho s will be what? It will be the charge density, r will be the radius of the shell, and P will be the distance at the small r from the center so that small r is greater than capital R. D psi is equal to d vector dot ds vector. So d into ds into ar cap into n cap. Here the dot product is 1. So d phi is d into capital D into ds. Total flux is integration of all. Remove the constant outside. Surface area of this pair is 4 pi r square. So finally total flux is d 4 pi r square. Equate it to the total charge, that is phi is equal to q. D 4 pi r square is equal to q. Substitute d as epsilon naught into E is equal to q divided by 4 pi r square. E is what? Q divided by 4 pi epsilon naught r square. E vector is q divided by 4 pi epsilon naught r square into ar cap. If the point P is on the shell, then the small r is equal to capital R. D psi is equal to d vector dot ds vector. The dot product is again 1. It is d into ds. Integrate. Psi is equal to q, d is equal to q divided by 4 pi r square. Finally, we'll get the equation. Next is P is inside the shell, so that capital R is greater than the small r. So same thing, d phi is equal to d into ds, dot product is 1. So psi is equal to integration of d psi, that is d into ds. So our ds is what? 4 pi r square here. According to the Gauss law, the total flux over a closed surface is due to the charges inside it. So d 4 pi r square is equal to 0. Then d is equal to 0, epsilon naught e is 0. So overall electric field will be 0. One application here we are going to learn here is about coaxial cable. Coaxial cable, cylindrical conductor. Consider a coaxial cable of what? Length L, inner radius of R1, that is a solid cylinder, outer radius of R2, that is an hollow cylinder. Assume that there is a positive charge enclosed over the surface of the inner cylinder. So what comes? So outer cylinder will have negative charge. What will be the charge density? Rho s. Then volume is 2 pi r1n. Total charge inside the cylinder is rho s 2 pi capital R1n. Now, if we consider R1 is less than this R, that is very much less than R2, then total flux over the Gaussian surface will be what? Now, in surface integral of d vector into ds vector is equal to total xi1 through the curve plus total xi2 of the both the flat ends. Here the dot, they are parallel to each other, d vector and n cap and d cap are parallel, so it is 0. We get d1 vector into ds vector is equal to d1 ds cos theta. Xi1 is equal to integration of d vector into ds vector. Xi1 is equal to d into 2 pi r. Next we'll go, that is d2 dot ds vector, that is equal to 0. So psi2 will be 0. On adding both the psi1 and psi2, we get d1 2 pi rl. Substitute d1 has epsilon naught e and simplify. Finally, equate it to the rho s into 2 pi r1n. You will get as epsilon naught into er is equal to rho s into r1. So my rho s is 1 by 2 pi r1 into rho l. Epsilon naught into er is equal to rho l divided by r, and r1 will get cancelled. E is equal to rho l divided by 2 pi r epsilon naught, that is rho l divided by 2 pi epsilon naught r into ar. If r is less than r1, then everything will be 0. If r is greater than r1 also, it becomes 0. The only case that exists here is if r lies between r1 and r2. Clear? So this was all about this module, this part. So next I'll continue the part 2 in the next video. Please do subscribe and share with your friends, and wait for the next upcoming videos. Thank you.